Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in week 5 and this is our first lecture. So in this week, we are going to learn column design, which we started in the previous week, but this time we will design a column with axial compression and uniaxial bending. Remember, in the previous week, we considered only axial compression and then we had minimum amount of eccentricity. But now let us consider if we have a column with axial compression and uniaxial bending. Now, let us first consider a cross section of the column. So, say this is the cross section. And it has the rebars. So these are some of the rebars. Now we have these rebars symmetrically placed on opposite faces. So these are the locations. It's a schematic diagram. So we'll see how to design their diameter, their spacing when we have bending on top of axial compression. Now, let's have these rebars on the opposite face as usual. And let us also draw the axis. So first we will go through the assumptions that we make before we design this column. Now, first thing is axial compression. So if you have axial compression, so we have the strain diagram for axial compression, and as you can see, it is uniform over the cross section. Now when we have bending, for that, the bending diagram, as you know, will have tension and compression, right? So let us draw that diagram. So typically this type of distribution we have, this is a schematic diagram. So at one end we have tension and the other end we have compression. Now for the complete section, as you can see, we have uniform compression and then due to bending we have tension compression. So the net stress or strain distribution will be a combination of these two. Now let us combine these two. For that, let our compression be positive. So on this side we have positive and on this side we have negative. And this is XU, right? Now for a column, we always wish to have no tension. So if that is the case, our strain diagram will be like this, right? Now in reality, it may not be always the case. We can have a different situation depending upon the XU that is marked. But for an ideal situation, obviously, we wish to have no tension in the column. So this is the XU. Now, let us first identify the assumptions that we are going to make. So assumptions. First assumption is plane section remains plane before and after bending. Second is compressive strength of concrete is 0.67 FCK, that you can recall from our previous discussion, with gamma MC is equal to 1.5. Therefore, the design strength is, it is 0.446 FCK. Now, stress in rebars are derived from stress strain curve. Next, maximum compression in concrete is 0.002. So here this value is 0.002. This is under axial condition, right? Next, maximum compressive strain under bending is 0.0035. So that means this one is 0.0035. When you can see here, this is what we call the location of the neutral axis. So that means when the neutral axis NA lies within the section. Now, in this case also, here you can see we have the combined action from axial and bending, and the XU is equal to D, right? That means the neutral axis is at the other extreme edge of the cross section. Now, if that is not the case, then what happens? For that, let us again draw this stress strain diagram, and then we will see how that happens. Okay, so let us copy this. So instead of having the neutral axis here, we'll have it somewhere here, right? So in that case, the location of the neutral axis is outside the section, and we have to now calculate the stress at this fiber. Okay. Now, if that is the case, then obviously this is no longer 0.0035. So this is 0.0035 minus 0.75 epsilon minimum. This is epsilon minimum. So We'll see why this is the case in a minute. But the assumption is that maximum compressive strain at the extreme fiber in compression is subjected to both compression and bending, where there is no tension in the section, and then the maximum strain is this quantity, 0.0035 minus 0.75 times epsilon minimum. So let us first see why that is the case, and then we'll move further. So what we do, let us copy this cross section. Let us redraw the strain diagram once more, and we'll see why we have that case when we have XU going beyond capital D. So let us draw this line, and for this case we have to draw the strain diagram once more. So this is 0.0035, and let us complete this strain diagram. So this is the case when we have XU equal to capital D, right? Now, the moment we have XU lying outside, so say this is the case, then we have to prove that maximum strain is 0.0035 minus 0.75 times epsilon minimum. So let us complete the diagram. So this is 0.0035, right? Now let us draw a vertical line here, and then complete it here. Okay. So now let us mark. So we have, say this point is A. Now this is the fulcrum point where we have the neutral axis. So this point is C, this point is D, and this is B. So this is D1 and this is D2. Sorry, the neutral axis is actually here. Okay. So this is the location of the neutral axis, and this is actually the fulcrum point. Okay. Now, say this is O. So CO, this is 0.002. And then if we mark the dimensions, so the total depth is capital D. So out of that, this is 3/7 of capital D, and this is 4/7 D. So the total depth is capital D, and total width is B, right? Okay. Now we have a loading point somewhere here. So this is the load acting with the eccentricity is E, right? Earlier we designed the column for minimum eccentricity. Now we have significant amount of eccentricity, and let us see how we can design this column. So now for But we have, say, look at AB, and also let us mark this point, say B2. So AB or epsilon max is equal to A B2, which is nothing but AB minus B. So what we get is 0.0035 minus B. Now, again, if you look at the strain diagram, what we have B2 divided by D2. Do not get confused with this D and this D here. This is the point at this corner. So this is equal to 3D by 7 divided by 4D by 7. So ultimately this is 0.75. So what we have BB2 is equal to 0.75 times we have epsilon mean. Therefore, our maximum is 0.0035 minus 0.75 times epsilon minimum. Okay. So the first conclusion is done. If we have XU is what? Let us mark XU. So this is XU. And as you can notice, neutral axis is lying outside the cross section. And this is XU minus D. Okay, so now the strain diagram is identified, and then let us see how we can move forward. Now, from this diagram, what we can notice that there can be multiple possibilities. Obviously, this XU can be less than this D, that is the cross section. In that case, it is well within the cross section. So let us first identify what are the possibilities. There are actually 4 possibilities. The first one is when we have 0 or minimum eccentricity. That means XU is equal to infinite. This case we have already solved in the previous week, right? So for minimum eccentricity, we have already designed. Second case, we have moderate eccentricity. And for that we have XU is greater than depth of the beam, column. So we have just noticed how the strain diagram looks like. The third option, again we have moderate eccentricity, which is a special case of the second option. It is XU is equal to D. So that means the neutral axis lying at the other end of the column. So this is the location. So if that is the case, XU equal to capital D, so that is the third case. And then fourth case, we have large eccentricity. And in this case, XU is less than capital E. As I said, we have already studied this in detail, so we will not discuss that. Our main focus is here when the XU is greater than D, and finally this one when XU is less than D. Now, this case is a special case. So once we solve case 2, we can easily solve case 3. So our focus will be to model the case 2 and case 4, right? Okay. Now, for this case, what we do, let us first consider the case. So case 2, we have XU greater than D. Now for this problem again, let us draw the stress strain diagram. So for that, let us copy this part. Now let us draw the stress diagram first, and then we will see how to find out the sectional capacity. We can easily draw the strain diagram because we have already identified the location of the fulcrum point and neutral axis. Let us complete the diagram first, and for that we already know what are the different level of stresses that we are going to encounter. So let us complete that diagram. So at the extreme compression side, we'll have 0.446 FCK. So this value is 0.446 FCK. Now it will be constant up to that point where we have the strain is 0.002, and beyond this we'll have parabolic profile. So that is the profile, right? Now the net compressive force will act somewhere here. We can use a opposite arrowhead. So let us draw the other way. And the location of this compressive force, you know, it is the CG of the stress block, which is at a distance, say C2 D. D is the total depth of the section. So this is our PUC. Now, because this is a parabolic profile, so we have to find out the stress at this rebar location. For that, what we do, we consider any point, say at a distance x. So let us mark it. Say this point is at a distance y, and this is x. So we can also evaluate the stress at this point. So this is, say, FC. Actually, our reference point is, this is at a distance A, and our reference point here, this is y, and we know this is parabola. So now we have the complete stress diagram, and we can derive the quantity. So for that we know XU is equal to K times D. If you recall your beam design, then let C1 be the coefficient of the area of the stress block. So now we know the equation of parabola. So equation of parabola is y equal to x square. So then let us complete this diagram. So this is y, and this change, this part, say this is delta. So delta, you can show that this is nothing but 4/7 d square, that is the x, right? Now we have another relation, so we have 0.446 FCK, which is equal to KD minus 3/7 d whole square. Notice this KD is equal to XU minus 3/7 d is the remaining part, that is 4/7 d, right? Now, say this is my equation 1 and this is equation 2. So if we divide equation 1 with equation 2, what we get? We get delta is equal to 0.446 FCK times 4/7K minus 3 whole square. It's very simple. We have this expression, we have this one, and the moment we divide 1/2, you can easily show this expression, right? Now, let us find out the area of the stress block. So for that, again, let us consider this stress diagram. So this area under the stress block will have a rectangular part plus a parabolic part. So if we find out area, A is equal to area of the stress block. So this is 0.446 FCK times D minus, so you can see it here. So you have 0.446 FCK times this D, which will give this complete area, minus this small wedge will give us the area of the stress block. So what we do, that is 1/3 delta that we have already find out times 4/7 d. So you can put the expression of this delta that we have here. So we have 0.446 FCK times d minus 1/3. In place of delta, we can write 0.446 FCK times 4/7K minus 3 times 4/7 d. This we can further simplify. So we have 0.446 FCK minus 1/3, or we can write it 4 by 21 times 0.446 FCK. Then we have 4 divided by 7K minus 3 whole square times D. So this in a compact form, we can write C1, that is the coefficient we have already defined, times D. So C1 is what? C1 is equal to 0.446. Sorry, here FCK is there. C1 is 0.446 minus 4 by 21, 0.446. So we can write 1 minus, and then we have 4 divided by 7K minus 3 square. Now this we can actually write in a more compact form. Often we see in design specification. So this is 1 minus C0 by 6, where C0 is equal to 8 by 7 times 4 by 7K minus 3 whole square. So we have identified C0, C1. We have another constant, that is C2 here, that will tell us the location of this PUC, right? And there are another constant C2 which is yet to be identified. But what you can see, for a given cross section, if we know what is this K, that is the location of XU, so we can identify C0, C1 at least, and then we can identify the area of the stress block, which is C1 times D times FCK. Right. So our next task is to find out this C2, that is the location of this compressive force. So for that, what we do, we actually take the moment. So if you have this stress block, we take the moment about extreme fiber in compression. So that is the location. So here, and if we do that, we have this entire stress block. So PUC times actually C2D is the moment. So for the area, we have stress block area times the lever arm C2D is the area of the stress block, right? Which is equal to 0.446 FCK times D times D by 2. That is the rectangular part. Okay. And then we have to subtract that extra wedge at the bottom that we have already considered. And for that, it will come 4 by 21 delta times D. Then within bracket, we have the location we can identify. It is 3/7 D. So this is 3/7 D plus the location of the CG of this parabolic wedge, which is 3/4 times the dimension, which is 4/7 D, right? So we can write that. So this is 3 by 7 D plus 3 by 4 times 4/7 D. Now, if we simplify, we have 0.446 FCK D square by 2 minus, we have 8 by 49 times delta times D square. In this expression, we can put the expression for delta which we do next. So we have here 0.446 FCK d square by 2 minus 8 by 49. In place of delta, we have 0.446 FCK, then 4 by 7K minus 3 whole square times d square. So let us simplify further. We have 0.446 FCK d square. Within bracket we have 0.5, and this remaining part we can write in a compact form C0 by 7. Right. So now we have the expression for C2. So C2 is 1 by AD times 0.446 FCK d square within bracket 0.5 minus C0 by 7. So this we can further simplify because we know this A is nothing but C1. So in place of A we can write C1 times D times FCK times D. So finally we can simplify it to 0.5 minus C0 by 7 divided by 1 minus C0 by 6. Recall, we have the expression for C1 that we have already derived here. We use this relation to finally simplify this. So we have the expression for C2 also. So now we have C0, C1, C2 all derived. So their values actually, if you look at, depend on what? Depend on the factor K. As of now, we don't know what is the location of K, and that is actually done iteratively. So we start with an assumption, then we verify whether that assumption is correct or not. Then iteratively we find out the location of the neutral axis, and then finally converge to the values of C0, C1 and C2. This will explain when we'll take the example. Okay. But remember that these values are dependent on K, and hence we need a iterative procedure to solve it. So once that is done, our remaining task is to find out the capacity of the section. So this capacity will be contributed by what? The concrete plus the capacity offered by steel. So if we go back to the cross section again, here we have identified all the parameters C0, C1, C2, and we have identified the area of the stress block. Our task is to actually find out this PUC. PUC we can easily find out because we know the stress block. So that gives us PUC. Now on top of that we have these steels also. So we have to take the capacity of the steel, and together they will give us the total capacity for this section. So ultimate capacity PU will be contributed by the concrete and the steel. Now for concrete, it is very easy. We know area of the stress block. This is C1 FCK times D times the width of the section is the total force, plus we have a layer of steels. So for that, let us mark, say this is the location of ith steel. So ith reinforcement. Now for the ith reinforcement, we'll have FSCI as the stress in steel rebar, and the surrounding concrete will have also the stress. So the difference of that stress is actually the net effective stress acting on these bars. So for that we have I equal to 1 to n, we can have n number of rebars. So ith row will have P times I, that is the percentage reinforcement, times BD divided by 100. So that is the area of the rebar at the ith layer. So you can see here, and then times the stress, which is FSCI minus FCI. We can write it, say, FSI. So this is the stress in rebar at the ith layer, and corresponding layer we can identify the stress in concrete. So remember this, we have to identify from the strain diagram. We'll do that in a minute. But now we have quantified the ultimate capacity of the section, which is given here. So as you can see, for this problem, we have quantified the axial capacity. Now the remaining part is the bending capacity, right? For that, again, we will take the moment of the forces about the neutral axis, and that will give us the moment capacity of the section. But before that, let us modify this. So Pu by FCK BD is equal to C1 plus I equal to 1 to n. We have Pi divided by 100 times FCK within bracket FSI minus FCI. Right? So this expression we see in the code where we have the contribution from steel and contribution from concrete. So this is from steel and this is from concrete. Now let us complete the remaining task, and for that mu, the moment capacity, mu is equal to muc plus mus. Again, this is from concrete and this is from steel. For that, what we have to do, we have to first identify the stress block, and now we know the location of the CG. So we have quantified this PUC, that is coming from the area of the stress block, times this C2D. We have already quantified C2. So C2D is the moment caused by this force about this fiber, where we have stress 0.446 FCK, right? So let us write that. So we have C1 FCK BD, that is the total compressive force, times D by 2 minus C2D. So we take the moment. So this is, let me write moment about neutral axis, right? So now let us again go back to this. So here is the neutral axis. We know C2D, so we can easily quantify the lever arm about the neutral axis. So we know the distance of this CG from the extreme fiber under compression, that is C2D, and we can easily quantify the lever arm about neutral axis. So that's what we have done here. Plus, we'll have the contribution from steel. So we have I equal to 1 to n Pi times BD divided by 100 times FSI minus FCI times the location of the ith steel, which is Yi. This we know because we propose the location of the steel, and the moment we propose, we know what is the Yi. So now we have the moment capacity, and this is again the expression that we see in Indian code. So we have mu by FCK BT square is equal to C1 times 0.5 minus C2 plus we have I equal to 1 to n Pi divided by 100 FCK times FSI minus FCI times Yi by D. So that completes the derivation. So we have the sectional capacity. But one thing we have to address here, how to find out FSI and FCI. So once we estimate FSI and FCI, that is the stress in the ith steel and stress in the concrete surrounding the ith steel, then we can easily evaluate the sectional capacity. For that, let us again go back to the strain diagram. So from this strain diagram, we can actually locate the strain at the ith rebar because we know the complete strain distribution over the section. And from that, once we identify the strain in the ith rebar, so epsilon I is equal to 0.002 times XU minus 0.5D plus Yi divided by XU minus 3/7 D. So this is a very simple exercise. We have earlier also done this. It comes from the strain diagram using strain profile from the strain diagram. I leave this as an exercise for you. So this is a home task. You just verify this. And the moment we identify this strain, we can actually quantify the stress in the steel because now we know at the ith layer the amount of strain, right? So if we refer to stress strain diagram, we can quantify this. So determine FSI from stress strain diagram of steel. Now recall earlier when we designed the beam, we considered this stress strain diagram of steel and that was idealized by the code, right? So in the code, we have this diagram available and from that diagram, you have to read and there are tables available also for that stress strain diagram. So the moment we quantify the strain from that table or the design stress strain curve given in IS 456, we can quantify the strain. So for Fe 250, if the strain is greater than 0.87 Fy divided by Es, that means yielding has occurred, then we consider FSI is equal to 0.87 Fy. If it is less than this value 0.87 Fy by Es, then we find out FSI as product of strain and Young's modulus. Right. Now for Fe 415, procedure is all the same, but for 415, epsilon I is greater than 0.8 times Fyd divided by Es. In that case, FSI from the table, and if it is less than this value divided by Es, then FSI is equal to epsilon I times Es. If Yd is equal to 0.87 87 Fy. Lastly, we have to determine FCI. Now, FCI is equal to, we know, 0.446 FCK minus 2 epsilon I divided by 0.002 minus, because we have that parabolic profile, this is for epsilon I less than equal to 0.002, and beyond that it is 0.446 FCK, where epsilon I is greater than equal to 0.002. Recall the stress diagram here. So in one part it is parabolic. So if by chance our still is in the parabolic region, so we have to find out the respective stress there. But if it is in this rectangular part, we can find out easily the stress in concrete. So that completes the exercise. So we know sectional capacity Pu, we know Mu, and then we can design the cross section. Remember, the location of the neutral axis K is obtained iteratively using iteration. Because at the beginning we don't know the location of the neutral axis, so we start with some assumption and then we iterate, and once the iteration converges, we evaluate Pu and Mu. Now, as I said, case 3 is a special case of case 2, so we don't need to separately derive the expression for them. In this case, if we put K equal to 1, we can get the sectional capacity for case 3. So with that, let us stop here. In our following class, we will see how to solve some problem, and also we have to derive the sectional capacity for the last case where we have large eccentricity. So that we will derive first, and then we will solve some example, and we will see how we can design a cross section where we have axial compression and uniaxial bending. Right. Thank you very much.